Hello and welcome to the Daily Space for today, Tuesday, August 11th, 2020. I'm your host, Dr. Pamela Gay, and I am here to put science in your brains. Today, after our regular news coverage, we'll be joined by Dr. David Grinspoon. Last week, David attended the Technoclimes workshop where a select group of researchers from around the world came together to try and define what we need to understand so we can go searching for other civilizations orbiting other stars. While we've long known looking for radio signals is a possibility, today we're finding a myriad of other technological possibilities, and we're going to learn what those possibilities are together right after the news. Today's headlines are all shouting a single name, Ceres. Originally thought to be a planet, this largest of all asteroids was visited by the Dawn spacecraft from 2015 to 2017. Even before Dawn entered orbit, we knew this world wasn't going to be a simple asteroid like we had expected. Bright and confusing spots were seen on the surface. Over the years, myriad papers have tried to explain this complex object. And this week, the journal Nature Astronomy has dedicated an entire issue to trying to explain this world. We couldn't fully read this issue prior to going live today, so we're only going to hit some of the highlights for now. On Thursday, we will have Georgia Tech postdoc and Dawn team member Kai Hewson join us to discuss results in greater detail. For now, this is what you need to know. Ceres is classified as an asteroid for the very simple reason that it is in the asteroid belt. This 588-mile across object is about 1/5 the size of Mercury, is in hydrostatic equilibrium, which is a fancy way of saying it is round. And it has complex geology that includes some tectonics that are driven by subsurface brines. Think super salty water instead of magma. The continued presence of liquid can be determined from gravity data collected by Dawn, and it appears this briny reserve is 25 miles deep and hundreds of miles across. The shiny spot that has so much captivated our attention is in the heart of Akator crater. Roughly 20 million years ago, we now think that something, most likely a smaller asteroid, hit Ceres and dug down through its surface towards the brine beneath. During impacts, all the kinetic energy from the asteroid's motion gets released as heat, shock waves, and other forms of energy that can together melt the impact site, which will later cool from the surface inwards, like a pie cooling from the crust, while leaving the pie's innards a hot, blazing, ready to burn your mouth substance. In the case of Ceres, this formed a cap over the now weakened region, and the salty fluid would erupt out through various parts of the 57-mile across crater floor, forming what are called Venalia facie. These erupting ice volcanoes are called cryovolcanos. Now, I'm amazed at how this worked. Over time, the subsurface melt also froze, and in combination with eruptions of fluid from deeper below, led to the formation of ocular craters dome. Now, these erupting brines, they left sodium carbonate, a compound of sodium, carbon, and oxygen on Ceres' surface. And it's these salts that are the super shiny substance on the surface of Ceres. Now, I'm going to put this a different way. Liquids got to the surface of Ceres two different ways. According to Dawn PI Carol Raymond, for the large deposit at Ceria Faculae, the bulk of the salts were supplied from a slushy area just beneath the surface that was melted by the heat of the impact that formed the crater about 20 million years ago. The impact heat subsided after a few million years, however, and the impact also created large fractures that could reach the deep, long-lived reservoir, allowing brine to continue percolating to the surface. Now, throughout this show, we have been showing amazing illustrations that were done by James Tuttle Keane. He regularly posts illustrations of science news on Twitter as J. Tuttle Keane, Keane. We will have links to all of these illustrations on our website, dailyspace.org. Now, one of the most exciting parts of this research to me is the evidence that these eruptions may be ongoing, with some of the features appearing to be less than 2 million years old and containing materials that can only survive on the surface for a few hundred years. According to the JPL press release, on Ceres' surface, salts bearing water quickly dehydrate within hundreds of years, but Dawn's measurements show they still have water. So the fluids must have reached the surface very recently. This is evidence both of the presence of liquid below the region of Achater crater and ongoing transfer of material from deep in the interior to the surface. This means that while the Dawn mission wasn't lucky enough to catch these cryovolcanoes in the process of erupting or oozing or slowly sending brines to the surface, we don't know the energy of this process. There could be salts continuing to make their way onto the surface today. And I, for one, can only hope that we get another mission returning to this world to explore the amazing geology it has to offer. Ceres is, in many ways, just as much an icy world as so many of the moons that we have studied orbiting Saturn and Jupiter. And while the icy moons of Saturn and Jupiter are amazingly active because of the gravitational influence that they suffer from as they orbit these gas giants, Ceres is out there, well, it's the biggest thing around itself. It doesn't have these tidal effects. This is a completely different way to be an icy body that we're just starting to understand. From the 2017 end of the Dawn mission to today, that's how long it took to get to this point of having enough research complete to create this special issue. This data is still going to be analyzed for years to come, but we need more data. So here's to hoping we get more missions. Now, that is all we have for today. As I said, this is a new issue. We didn't have time to make it through the entire issue before going live with this episode. On Thursday, we are coming back with one of the researchers who works on the Dawn mission from Georgia Tech, and she's going to be helping us understand even more than what I could bring you today. Now, before getting to your guest, I have one final reminder. There is a meteor shower going on if you are lucky enough to be someplace with clear skies. Tomorrow morning before the sun rises, there will be a whole lot of meteors and also a whole lot of moon. If you go out earlier in the evening before the moon rises, you'll still see a whole bunch of shooting stars, just not as many as you would in the early morning if there was no moon. Sometimes meteor showers aren't as friendly as other times. This is an excuse, however, for you to get out your hammock, get out your lawn chair, get out your sleeping bag, go lie down, make sure you're covered in enough bug spray, and just take in the summer skies. And remember, as you're looking at all those stars, that a whole lot of those stars are supporting planets. Maybe even most of those stars are supporting planets. And we don't know how much life may or may not be out there. But if it's out there, in just a few minutes, we're going to be discussing how it is that we may be able to find it. So stay with me. We will be joined in just a moment by Dr. David Grinspoon, and we're going to talk about how we can find potential civilizations orbiting distant stars. Thank you, and stay right where you are. Hello, everyone, and welcome back. I am now joined by Dr. David Grinspoon. How are you doing, David?
Hi, Pamela. I'm fine. Considering one has to add that these days, but no, I'm doing all right. Thanks.
This is true. This is true. Life is certainly odd nowadays, and it must have been frustrating last week to attend this amazing conference and not be able to do it face to face. Can you tell everyone about the Technoclimbs meeting you were at?
Yes, last week I, attended in air quotes a really cool workshop, very innovative and unusual. It was the title was Technoclimbs, which refers to the renewed effort to look for technosignatures, that is, signs of intelligent life and technology elsewhere in the universe. And the climbs part sort of refers to the fact that there's a renewed effort to consider exoplanets and what the signs of an inhabited exoplanet, not just inhabited, but inhabited by a technological civilization, what the observable signs of that might be. And so it was an interesting mixture of people that think about climate modeling and what the signs of a managed climate might look like, in addition to sort of more traditional SETI, that is, search for extraterrestrial intelligence scientists. And so it was an interesting mix of minds, a really cool gathering of people combining a lot of different points of view and scientific backgrounds to sort of take a new stab at this question of, how might we be able to find the aliens?
And we've long thought about going and looking for radio signals that get leaked, especially during the early days of a civilization when everyone has omnidirectional television broadcasts and radio broadcasts instead of the uh, cable access we all have today. Um, but this meeting specifically said not talking about radio. So what are the other ways that we go looking for technology?
Yeah, I mean, it was interesting that it was a focus on non-radio
Yeah.
technosignatures. And the purpose of that, it wasn't like we've decided that it's not worth looking for radio. In a certain sense, the search for radio signals is still very new and hasn't been done very thoroughly. And it wasn't saying, okay, we're going to give up on that. It was just saying, now that we've got all this new knowledge of exoplanets and we have new ways to observe them, and that just the idea was broadening the search, not giving up on the old search. So there were some representatives there of what you might consider old school SETI
Yeah.
radio searches, and obviously that wasn't off limits. It wasn't like you were not allowed to mention radio. It was just like, hey, how do we broaden the search? So one big area was thinking about exoplanets and all the new techniques that are coming online and imagined in the near future to observe planets around other stars. Because the idea is, since we're going to be searching them anyways for biosignatures, signs of life, then why not, while we're looking at them, consider how we might recognize technosignatures? And the very word technosignatures is sort of consciously, in parallel with biosignatures.
Right.
And on the one hand, okay, maybe it's crazy to think about that. On the other hand, if you think about evolution of life, and it's just sort of a stage in a planet going from being lifeless to having life that you could observe, you might imagine that some planets, in parallel with Earth history, then develop complex life and maybe even communicative technological life. So, there's nothing crazy about it, even though it sounds, fantastical and science fictional. There's a lot of emphasis on, okay, how would you spectroscopically see signs? What might technological civilizations be putting into their atmospheres that you could observe? There were questions of city lights. What are the limits if you imagine a planet that's really highly urbanized and really highly lit up, which of course makes the astronomers listening really nervous. Like, why would you want to live on a planet like that? But you could sort of,
Coruscant, though. We've all seen it in the Star
right.
Wars universe. We're looking for Coruscant.
Yeah, exactly. So what are the limits on how you would spot that? And then a lot of imaginative ideas were put out there. Jill Tarter, who's sort of a hero of SETI, was there, and she I hesitate to say old school because Jill is sort of eternally youthful, and but she's been on the guard of SETI for a long time, the traditional radio SETI. But she was right there with all kinds of new ideas,
Yeah.
looking for what she refers to, in reference to Arthur C. Clarke, as a Clarke exobelt. The idea that if a planet with technological civilization has enough stuff in orbit, then that forms kind of an exobelt, and you might see the sort of the signs in the light curve, or some other detectable signs of just all that stuff orbiting in between you and that planet. So there, and then there's some more far out sounding stuff too, like searching for artifacts in our own solar system. And it's was pointed out, and it's pretty easy to show quantitatively, that our solar system has not been well searched
Yeah.
for artifacts. Even the surface of the moon and the surface of Mars, there could be fairly large things that have not been really detected yet. And this verges into the sort of woo area, and a lot of scientists are reluctant to talk about it because you can go online and you can find all kinds of websites that show you that they found cities and elephants and
Right.
whatever on Mars. And so, one of the challenges of this field is, how do you talk about this stuff in a way that doesn't invite woo,
Yes.
but also you don't get scared off by the potential for woo, so that you don't talk about things that legitimately ought to be searched for. So, there was some talk at this meeting also about sort of how do you draw those boundaries.
And it seems like what you're really getting at is all the different stages that civilization go through are detectable in different ways. I can imagine our own Earth was much easier to atmospherically detect back when we were in the Industrial Revolution and it was coal soot all the way down. And so you have that period during which you pollute your atmosphere, and then hopefully you get yourself together as a civilization and you stop that and you get a clean atmosphere. But at that point, maybe you filled geosynchronous orbits so full of stuff that it's like a ring around a world. And then eventually you're building those von Neumann probes that maybe there's one sitting on Mars waiting for us to find. Is this a fairly good way to look at it? That
Yeah, I mean, I'm not sure, you can't necessarily predict a sequence of
right,
stages, but
right.
certainly those are all potential manifestations of technological activity that would create some kind of observable signature. And it's funny, the idea of pollution, thinking of that, because this topic leads automatically to the question, what are the properties of long-lived civilizations? Because when you do the math of SETI, you realize the short-lived civilizations are going to be really hard to find.
Right.
Just statistically, you'd have to catch them at the right moment, and you're not likely to. So it's the really long-lived civilizations that overwhelmingly, statistically, you're much more likely to find. What are the properties of long-lived civilizations? They probably don't wantonly pollute their atmospheres in certain ways that would lead them to not be long-lived civilizations. So, one of the interesting and potentially very useful aspects of this field is it gets you to think about the whole question of sustainability in a different way. If we are to have a really long-lived civilization, what would our relationship with our planet be like? And what might we look like to an alien? And by
Yeah.
the same token, if we think of long-lived civilizations, what might their properties be? And then you get to things like interesting ideas about terraforming. Can we find climates that have been managed somewhat
Yeah.
in other solar systems? And there's some fun variants of that. What if you find multiple planets in a system that all have suspiciously similar climates? Like somebody there likes the climate that way, and they're like, wow, how odd, an Earth and a Mars that have exactly the same climate. How would that have happened? So there's some fun ideas, but then you get to this whole other almost philosophical question of how much can we second guess the aliens? If you think about the fact that it's so hard for us, really impossible, to predict our own technology 100 years from now, 1,000 years from now, 1,000,000 years from now, if we're still here, forget it. And that's predicting the future on Earth. Now imagine trying to predict technology on another planet that doesn't have the same origins as we.
Right.
And so to some degree, you try to find these sort of general principles that might be followed that you could predict. But then there was a lot of interesting discussion of how much the search should be hypothesis driven versus just exploratory. Meaning, if it's hypothesis driven, then you have a specific idea. Aliens, if they exist, probably would behave this way and would have this kind of signature. Let's look for it. And that has the advantage that it's easier to do science when you have a
Yes.
hypothesis you're trying to, refute or confirm. But as a disadvantage, then we're having the hubris to imagine we can second guess the aliens. So there's this whole other idea that, well, we should just collect a lot of data and look for anomalies, which is might be the way to find them. But then how do you justify that as a research program? We're just going to look around and hope we find something weird. So, so this was one of the sort of
Yes.
meta topics at this conference. This really interesting conference was like, how do we balance these approaches and sort of do science, but not assume we know more about aliens than we have any right to really assume?
And and the amazing thing about this is we are constantly learning that we're not creative enough to guess what the universe is going to do. And so not just aliens, but like base physics keeps finding more creative ways to generate galaxies, more creative ways to assemble solar systems than what we initially imagined in building our models. And so to realize that we are over limiting in how we imagine physics working, and then to try and factor in imagining how biology works. It does require a certain amount of hubris,
Yeah.
but at the same time, the other problem with the broad survey of let's just look for weird stuff is the whole if weird stuff is found, someone's going to try and solve it using physics rather than biology. We had all of the excitement of Tabby's star a number of years ago, And there was, for that moment in time, the possibility that this was a megastructure in the process of being formed. And the rest of the community was very much like, no, we do not want to discuss this. While there was those few people willing to say, we have to discuss this. And it wasn't true, but we had to have the discussion. Well, how do you get funding to purposefully look for the weird objects and build a team capable of having that combination of people that are both skeptical but willing to say we have to ask the question?
Yeah, I mean, as you say, even when we're not talking about aliens, there's this tension between hypothesis-driven versus just exploring. I've been involved in a lot of proposals of planetary missions, most of which don't get funded, but once in a while one does, yay. And there's always this tension even in planning a mission because you have to have specific hypotheses that you're going to test. Say you're going to Mars, you can't just say, well, we want to build these instruments and go try to find some cool stuff. You say, well, here's our idea and here's the instruments that can test it. And, you sort of pretend it's all hypothesis driven, and some of it is, but a lot of the value comes from just exploration and finding
Yeah.
things you didn't expect. I mean, you just gave us this amazing introduction to the new findings on Ceres, which is a great example. Nobody said we want to send a mission to Ceres because we have a hypothesis that we're going to find these weird white spots that indicate this whole hydrologic system that nobody ever previously suspected. They said we're going to go to Ceres with cameras and this and that, and we're going to study it and blah blah blah. And then of course you find the amazing thing that revolutionizes what you think about small bodies. That that's really anomaly detection.
Yeah.
But you can't justify a scientific program based on that, even though that's often what the benefit turns out to be. Now, with the example you gave of Tabby Star, and then another example I would put in sort of that same category is Oumuamua,
Yes.
which was this weird thing that came in from beyond the solar system that had properties nobody had predicted, that some scientists, some reputable scientists said, well, if this thing was an alien artifact, it would explain these weird properties.
Yeah.
Now, neither Tabby Star nor Oumuamua turns out probably to be an alien artifact, although there's still probably some holdouts for both of those. But they're both cases where that was not a ridiculous hypothesis
Right.
because there were weird things that didn't make sense according to what we were expecting to find, with these kind of observations, and that even conformed to some predictions that had been made. In the case of Tabby Star, there was the idea of a Dyson sphere. This wasn't exactly like a Dyson sphere, but the idea that you could have extended stuff in orbit around a star that would block the star sometimes and would not behave like a planet because it appeared to be some huge extended thing. So it was not a ridiculous thing to claim, but it was very interesting watching the scientific community then try to wrestle with that. And some people said like, oh, no matter what, you're always going to say aliens,
And
which
there
you
are
don't.
other people who, no matter what, are going to say physics.
Right. And so it's very instructive, because if we ever do find an artifact, there are going to be people that say, oh, that's ridiculous, it's physics. And that's okay. I think that back and forth, that tension is good. It should be the hypothesis of last resort,
Yes.
or to use the famous Saganism, extraordinary claims do require extraordinary evidence. So if you're going to claim something like that, then you have to expect people are going to come back and say, oh no, physics. And then if they can explain it with physics, fine. But people are going to try, and if they try and try and try and can't, then you still don't say, well, then it's got to be aliens. But then you say, okay, it could be aliens. What other observations could we do to test this alien idea? At least it stays in the column of plausible, and then you devise other ways to try to confirm that.
And we're going to go to take questions from our audience in just a moment. Before we do that, what what do you think is going to be the next biggest thing that we purposefully go looking for now that we've been looking for radio signals? What do we look for next to try and find civilizations among the stars?
Well, first of all, a lot of what we ought to do is kind of commensal observations, things that we're going to do anyways, but make sure that we don't rule out the exotic possibilities by not searching in the right way. So some of what we're doing in the solar system, whenever we do high resolution imaging of a new object, we should make sure to be open to this possibility. But as far as what's really coming up and going to be new that could produce technosignature observations, I would point to the kind of next generation space telescope spectroscopic observations that we're going to be doing anyways of exoplanets to try to find biosignatures, and simply with that search make sure that we're doing the right kind of coverage and the right kind of spectral zones and the right kind of analyses to possibly also turn up technosignatures while we're going to be looking at these exoplanets with everything we can anyways, because we need to. So let's also look for technosignatures.
So, good science will lead us not just to a better understanding of the chemistry of atmospheres, but also to the potential for life on those worlds.
Yeah, and even the potential for somebody who's home and building things and modifying their planet with machines for better or worse.
And sometimes for better or worse is the best description we have of our civilization. Um,
Indeed.
and this is amazing. And to those of you who are watching this and not watching it live, there are going to be questions that you can follow along at twitch.tv/CosmoQuestX here on the Daily Space.